Okay, so let us look at a few examples of homeomorphisms. All right. Now, first, let me show you that all open intervals are homeomorphic to the interval from 0 to 1 and hence to each other. By the way, I wrote hence to each other, right? So, but what I'm implicitly assuming here, and I didn't prove it, is that being homeomorphic is an equivalence relation, right? So it must be symmetric, reflexive, and transitive. So you can think about why this is so at home. It is a very good exercise, right? But believe me, it is an equivalence relation. So if all open intervals are homeomorphic to 0, 1, it means that they will be homeomorphic to each other. So how can we prove it, right? So suppose that we have an interval from A to B, right? And we want to construct a homeomorphism from this interval from A to B. To the interval 0, 1, right? So 0, 1. So a homeomorphism is supposed to be a bijective function, continuous, and the inverse is also continuous. The easiest thing to do is to try a linear function, of course, right? So let me just try this. So f of x is, so we want to construct a linear function that sends basically a to 0, b to 1. Well, and if you think a little bit, you will realize that this should be the function x minus a over b minus a. Indeed, so this is a linear function, so it is definitely 1 to 1. So in order to see that it is a homeomorphism, it is increasing, so the inverse function is also linear and is also increasing. So in order to see that it is a homeomorphism, it is sufficient just to establish that f of a is 0 and f of b is 1, right? So, and we can check it directly. So f of a is, we are going to substitute a instead of x. So this is a minus a divided by b minus a is 0. Check. F of b. Now we are substituting b as x, so b minus a over b minus a is 1. Check. So it is indeed so. So the graph of this function looks like this. So if this is, I don't know, AB, this is 0, 1. So this is what it looks like. Okay. Next, all open intervals are homeomorphic to the whole real line. Wow. So small finite open intervals are going to be homeomorphic to the infinite real line. But this is still true. And what I'm going to do, I'm going to give you the example of the homeomorphism first, and then we will figure out what the open interval is. So the homeomorphism here is going to be f of x is tangent x. Right? So the graph of this tangent function looks like this. I hope you still remember from secondary school. So this is negative pi over 2. This is pi over 2. Right? So this means that my tangent function is a homeomorphism from the interval from negative pi over 2 to pi over 2 to the whole real line. So from negative infinity to infinity. And of course, the inverse function is the inverse tangent. And it is going to be the homeomorphism from the real line to this interval from negative pi over 2 to pi over 2. Okay, done. So a square is homeomorphic to a circle. Wow, how can we do that? Now, so notice that in the first two examples, we were able to construct an explicit homeomorphism and the inverse function. Well, I didn't really write it down, but it was also easy to construct. So in this case, it is relatively easy to construct a homeomorphism from the square to the circle, but vice versa is a little bit more challenging. I mean, I'm not going to explicitly write the inverse function, but the direct function is not too hard, right? So these are going to be our coordinate axes. So let me draw a circle. So a circle is given by the equation x squared plus y square is 1. So if our coordinate axes are x and y. And let me draw a square now. Okay. And let me kind of schematically show my homeomorphism, right? So the idea is that if my point on the square is here, I'm going to connect it, to join it to the origin. And if this is my x, then this is going to be my f of x. Well, but my x is not really, since we're dealing with the plane, it's probably more convenient to write like xy. And this is going to be f of like f of xy. So meaning that xy represents a single point on with coordinates x and y on the plane. It is a single point on the square, or it is a single point on the circle, right? So my f of xy is therefore going to be, watch this, is going to be x over square root of x squared plus y squared, comma, y over square root of x squared plus y squared. So why did I write this? Because now imagine that, how do we verify if some point on the plane belongs to the circle, right? So we need to take the sum of squares of its coordinates, of x and y coordinates, and see if there's one. And now, if I square this plus this squared, I'm going to get 1, right? So which means that whatever is written here is indeed a point on the unit circle. So what I just did, I have verified that such a constructed f is indeed a function from the square to the circle. I did not really prove that it is bijective. So the fact that it is bijective should be obvious from the picture. I did not prove that it is continuous. Well, but if you look at it, you will see that it is given by a single formula. So we know from calculus that it is continuous. So the only thing that remains to show is to prove that the inverse function is continuous. So the inverse function goes like this, right? So if we take any point on the circle, then we should join it to the origin, extend this, and see where it intersects. And this is going to be the image of our inverse function on the square. It is kind of clear here. I'm not going to do it rigorously, and you will see that most of the time in topology we don't really, at least on this level, we don't really do things very rigorously. So if we see that it kind of makes sense from the picture, then we just say, okay, it's done, it's correct. So this is the first example where I did not really write down explicitly all the details, but you see that it is indeed a homeomorphism. All right. Next example, any smooth, closed, simple curve. It is also called a knot, is homeomorphic to just the unit circle. So here is one example of a knot in the 3D space. And let me show you what this homeomorphism is going to look like, right? So basically, I'm not going to be able to write it down explicitly again. So I'm going to just show it to you, right? So if we have a knot that looks like this, what we can do is we can undo it somewhere. Then we just untie it. And then we glue it back together. And we get a circle. So this is a homeomorphism, right? So because in this operation, we just did a little bit of stretching, turning around, and we did like cutting, but then we glued it back together at the same place. So which means that points that were close to each other initially, like, I don't know, these 2 points, this and these points were initially close to each other, but in the end they are again close to each other. So this is still a continuous deformation. Well, in the next example, we are going to see that a half open interval is not homeomorphic to a circle. Well, let me first explain why do we think that it may be homeomorphic to a circle. So why did we even come up with this ridiculous idea that a half open interval is homeomorphic to a circle? And the idea is that so we can think of our half open interval as the interval from 0 to 2 pi, and consider a point theta in this half open interval, and consider this function that sends theta to cosine theta and sine theta on the plane, right? So this is a point on the plane. And geometrically, right, so we have our half open interval from 0 to 2 pi. And the image of this function is nothing else but our unit circle in the plane xy. Yeah, because cosine square plus sine square is 1. Well, at the same time, we know from secondary school that if theta goes from 0 to 2 pi, then this point cosine theta, sine theta, it just goes around the full circle, and these are polar coordinates. Now, this function is 1-to-1. And this function is onto, so it is a bijection. This function is continuous. But is it a homeomorphism? The answer is no, because the inverse function is not continuous. So the inverse function is not continuous. So let me explain why, right? So consider like these 2 points here and here on the circle. So on the circle, they're close to each other. But the inverse function from the circle to the half interval sends them to points that are far from each other. And so which means that the inverse function is discontinuous, right? So this is not a homeomorphism. But does it mean that our half open interval is not homeomorphic to a circle? Of course not. It just means that maybe we are stupid and we failed to construct a proper homeomorphism. So maybe that there is someone smarter could construct a homeomorphism, right? So how can we show that something is not homeomorphic to something else? Well, the idea here is that, so if, let's look at our open interval. So imagine that you took scissors and you cut this open interval somewhere in the middle into 2 parts, right? So you kind of remove this point in the middle, and what remains, it just falls apart. So it just falls apart into 2 intervals that look like this. I'm sorry. So if you remove 1 point, then the remaining interval falls apart into 2 intervals. One of them is half open, the other one is open. But if you take a circle and cut it somewhere in the middle, then what you will get is, well, basically this point is not there. So it means that you can kind of open it up and you will get a single interval. So it does not fall apart. That's the point. So if you cut a circle somewhere in the middle, it's not going to fall apart. But if you cut an interval somewhere in the middle, then it falls apart. Okay, so which shows us that they are not homeomorphic.